the definition or the formulation of Maxwell equation in integral form. These are the four Maxwell equations in integral form, and also we have the continuity equation, which can be derived from the differential form as we have seen before. So we have here Faraday's law, Ampere's law, and Gauss law for electric field, the Gauss law for magnetic field, and the continuity equation. Where is electric displacement current? You see the electric displacement current here, which is a partial D, partial T. This is the electric displacement current density. We can say GD, which is partial D, partial T. And where is the displacement magnetic current density? Very similar to the displacement electric current density. So the displacement electric current density is the change in the electric flux. The displacement magnetic current density is the change in the magnetic flux density with time, which doesn't exist, but we are assuming that this change here, partial D, partial T, does represent the displacement magnetic current density. And the partial D, partial T is the displacement electric current density, which does exist between the two plates of the capacitor, or this is the dominant current in dielectric in general. So these are the differential form, and these are the integral form. How can we go from here to here, or from here to here? And how can we derive each one from the other? By using both Stokes theorem and divergence theorem. You can easily go from here to here or here to here. You can take the divergence of this guy, and then using Stokes theorem, this will be transformed to the circulation. You can easily go from here to here. In what situation or in what kind of problem we can use the differential form to work with, or use integral form? And when can we use this, and when can we use this? Actually, the differential form are derived from the integral form on the assumption that the field are continuous, single valued, bounded. Bounded means the field value cannot go to infinity. And also the change in the field is always continuous. So if you look, say, at the relation between, do you remember the equation, the voltage across the inductance field, LdI by dt? Look at this equation. Can we have sudden change in the current? Yani can we have I versus T to be something like this? Can we have this? Why? At this time, what is the voltage? Infinity. The I by dt here at this time is infinity. So it will give a non-realistic solution. The same for the differential form. The differential form cannot be working if you have Ex, for example, if you have Ex versus X to be something like this. How can we take the divergence here, or the curl? It's a derivative, right? Divergence and the curl is always derivative. So it will lead, and if you take here dEx by dx, this will be infinity. This means the flux will be infinity, the magnetic flux will be infinity. So the differential form must be used if you know that the field are continuous. The field is always continuous, the electric field, magnetic field, and the flux also continuous, and also differentiable. And also the first derivative, at least, is always continuous. So there are some situations that we cannot use the differential form, like at the boundary condition. If you have like two different media, and the field is traveling in between, so due to the discontinuous field distribution or the current distribution at the surface between the two media, this equation will not work, because you will have something like sudden change in the field. But the integral form are always valid in any situation. Actually, the dominant, the mother form is integral form. This guy is special case. Only if the field are continuous, single valued, so it has only single value at the same point, at the same time, bounded and differentiable as well. But when we think about which one is easier to use, which one is easier to work with? Differentiation, which is always easier. So if you have this condition, you can use the differential form. It will be much easier than the integral form. But in some situation, you have no choice but use the integral form, especially when studying the field traveling between two media. If you have two different medium and the field is traveling, and you need to find the relation between the field at the boundary, you must use the integral form. So this takes us to the constitutive parameters. So any material contains a charged particle, right? Electrons, protons. Once the electromagnetic field is incident on this material, the charged particle are going to interact with this electromagnetic field, changing the performance or the behavior of the material in response to this electromagnetic field. So to take this study from microscopic scale, where the charge or the atomic structure are very small, to a bigger scale, we need to use what we call constitutive parameters, which is mu, epsilon, sigma. This will let us understand how the material would interact with the incident or the external magnetic field and the electric field. So we mainly have three parameters and three relation, as you know, as we discussed before. So the electric flux density is proportional to the electric field by the parameter called epsilon or permittivity. B is mu h. J, the conduction electric current density, equal to sigma, which is the conductivity, times E. Do you know what is this? What's this star? It's convolution. Why use convolution here? Because everything is time dependent. The flux, the field, and epsilon are time dependent. So basically, the electric flux here does depend on the instantaneous value of the electric field and the previous value and the history of the electric field. To account for this, we must use convolution. Convolution is like time integral, which over, to expand this convolution, it will be like integration minus infinity to t, epsilon t minus tau times e. This is convolution. So it does depend on the electric field at all times, actually, or the instantaneous value and the previous value. So the material has a memory. Okay, so we must study the previous value of the electric field to find the instantaneous value of the magnetic flux. But if we go to frequency domain, from time domain to frequency domain, or if we are studying single frequency operation, so the convolution now has no meaning. We can remove the convolution, it will be just a multiplication. Okay, if we are working in frequency domain, and this is what we will do. Likely, this is what we will do from now on. We are going to focus on frequency domain, single frequency operation. So you don't need convolution. It will be at single frequency. All this will be multiplication. So we can now characterize or classify material in terms of the behavior in response to external electromagnetic field to be dielectric insulator, where the behavior will be mainly based on the electric displacement current density or polarization of the atomic structure. This will cause the electric displacement current density to be the predominant phenomena here. We don't have conduction current here in dielectric, like the current between the two plates. In magnetics in general, so the predominant phenomena is the magnetic displacement current density, which what we call magnetic polarization as well. So this guy is electric polarization, magnetic polarization, or magnetization. We're going to expand on this topic in chapter 2. We're going to study how the material can be polarized in terms of electric field and magnetic field. In both conductor, the predominant phenomena is the conduction current density, because here we have electrons moving in some conductor. Semiconductor, this is like the gap between dielectric and the conductor, and neither of these are dominant in semiconductor. Neither of these current density are predominant in semiconductor. So our focus in chapter 2 will be dielectric, magnetics, and the conductor. We're not going to focus on semiconductor. I think we take this in other courses. So this is what I said. So looking here at the differential form of Maxwell equation in time domain, we can, this guy is the magnetic displacement current density, and we can now replace the conduction electric current density by sigma E, based on the constitutive relation we have taken. And also this is a displacement electric current density, as we know. We can now use time harmonic, so assuming the field is sinusoidally changing by time, sinusoidal waveform, so it will be proportional to e to the power j omega t. And then we are going to use phasor domain. In phasor domain, the derivative of partial t e to the power j omega will be same as j omega. So we can remove partial t by j omega. So I'm moving from time domain to time harmonic or sinusoidal behavior, frequency in this frequency domain, based on single frequency operation. So any change in e to the power j omega t will be partial partial t. Partial partial t will be j omega. So now we can replace partial partial t by j omega, as we can see here, and the equation will be similar. Curl H will be the embraced electric current density plus sigma plus j omega epsilon times E. And I am going to remove partial partial t, replace it by j omega, assuming we have sinusoidal variation of the field with time. Okay.
In previous slide, we have two extra terms, mi and ji. You did not.
In this slide?
Yes, mi and ji. First question. What?
This one?
Yes.
This is embraced magnetic current. Okay. This is like a magnetic current source, a physical source you add in the circuit. And this also embraced electric current, physical source. We can also classify the material based on the frequency and the value of sigma. This ratio is called the loss tangent, as we will take later. So if the loss tangent, if the ratio sigma over omega epsilon is very large, almost infinity, this is perfect conductor. If the ratio much bigger than 1, not infinity, good conductor. Semiconductor somewhere here in between. Good dielectric, this ratio will be much less than 1. If the ratio is 0, if the conductivity is 0, regardless of the frequency, this will be perfect dielectric. So we can classify the material based on the sigma and omega, as you can see, based on the conductivity and the frequency. And that's called the loss tangent, as we'll see later in chapter 3, I believe. We can also characterize the material based on the response of the constitutive parameter. The constitutive parameter, as we said, is epsilon mu sigma. So this parameter, epsilon mu sigma, does respond in a different way to frequency, to magnitude of the field, direction of the field. So we have 3 parameters that can control these values. This takes us to this classification. So we have linear, non-linear material, homogeneous, inhomogeneous, isotropic, non-isotropic, dispersive, and non-dispersive. So what is the difference between linear and the non-linear material? Follow?
Superposition and homogeneity property that can satisfy that.
So the relation between the electric flux density and the electric field will be linear. Actually, it's based on the relation of D and E. So if this relation is linear, like this, D is epsilon E. So if epsilon is like constant, so D and E will be, the ratio will be linear. Otherwise, it will be non-linear. And in the linear relation, in the linear material, the constitutive parameter will be independent of the applied field. So regardless of the applied E and H, this parameter will be the same. This will be linear material. Epsilon will be constant regardless of the field. Otherwise, it will be non-linear. If the constitutive parameter, if this parameter change with the electric field and magnetic field, so it is non-linear material. So most material are linear, and the material we see around are linear. Give me one example of non-linear material where this parameter change with the applied field. Do you know lightning? So what happens in lightning, in this spark between the earth and the sky? Actually, the air, if the air is exposed to extremely large electric fields, like 10⁶ volt per meter, the air will break down. Break down means the air molecules will be ionized. So it will release electrons and protons. So the air start to be conductor if exposed to very high electric field. And that's what happens in lightning. In lightning, due to the huge difference between the charge in the current and the earth, the air will be like conductor. It will allow the current to go through because we have huge amount of electric field. In this case, the ratio will be nonlinear, and the material will be, these values will be based on the applied electric field. If the field become very large, applying on air, for example. And also some optical material are nonlinear. We have also homogeneous, non-homogeneous. So homogeneous material means the constitutive parameter are independent of the position, not function of position. So at any place in the material, you have the same epsilon mu sigma, which like all the stuff around. Non-homogeneous material, the constitutive parameter will be based on the position, like what? What material is inhomogeneous? Graded index optical fiber. In optical fiber, based on the location, you will have different constitutive parameter based on the position in the optical fiber. We have also dispersive, non-dispersive. So dispersive material, the constitutive parameter will be based on frequency. So these parameters will change by frequency. If they are constant, regardless of frequency, they are non-dispersive. Okay? Can you give me an example of dispersive material? Will this parameter change with frequency? Microstrip transmission line. To some extent, yes. What else? What common material we see around which is dispersive? You know glass? Glass is dispersive material. So it is transparent at visible wavelength, but if you go for ultraviolet and infrared, it will be opaque. Opaque means glass does not transport light in the ultraviolet and the infrared. So at these frequencies, compared with the visible wavelengths or RF and microwave, the glass will be non-transparent in the ultraviolet and infrared. So the glass is non-dispersive material. Sorry, dispersive material. We have also isotropic and non-isotropic. So isotropic material, when the constitutive parameter are function of the direction of the applied field. So based on the direction of the applied field, say the electric field in X direction, we will have different constitutive parameter. Okay? Otherwise, it will be non-isotropic. Like what example of isotropic material? Or sorry, non-isotropic material. What example of non-isotropic material? Where the material, the constitutive parameter are function of the frequency, function of the direction of the applied electric field. So, what material is non-isotropic or anisotropic? Ferrite, yes. What else? Crystals in general, like quartz and calcite or calcite is a dispersive material. Sorry, non-isotropic material. Okay. Again, this is comparison between the differential and the integral form. Now we can see that Maxwell equation can be used to describe electric circuit behavior. Yani we can express Maxwell equation, specifically Faraday's law and Ampere's law, as circuit equation, or it will be referred to circuit quantities, as we'll see. So this is Faraday's law. The circulation of the electric field around any closed path can be expressed as a summation or the algebraic summation of the voltage across this closed path, right? E dot dl is a potential, electric potential. So we can express this circulation as a summation of the voltage, assuming the voltage drop from positive to negative, and we need to take care of the polarity around this closed path. And this will equal to the negative of the integration of BDS minus the embraced magnetic current. Assuming we don't have embraced or magnetic current source, so we can cancel MI. In this case, the unit of this part, the unit of this is voltage, right? The unit of all of this. So we can express this voltage or this electric potential as the change of the magnetic flux with time. This also has the unit of voltage. And the magnetic flux can be expressed as the time, as the current times some stray inductance. Stray inductance, LS, is like the inductance of all the conductor and the wires in the circuit. So it's unintended inductance. And assuming we have our LC circuit with some source, LS here represents the inductance of all these wires. It will be very effective at high frequency. At low frequency, this can be zero. But at high frequency, this will be very effective. You cannot ignore it. So assuming all these conductors have some LS or stray inductance, we can replace the magnetic flux by LS times I. And then we can take LS outside. So now the summation of the voltage around this closed path will equal to negative LS partial I partial T, which is the voltage across an inductance, which is this inductance in this circuit. So this is a field relation, which is based on E and B, and this is a circuit relation based on V and I. They are the same. They are very similar. and you can extract this equation from the field relation. Okay, this is a circuit relation derived from Maxwell equation. Example like this example, we have here some embraced source or LC that you added, and we have the stray inductance. So by using this relation, we have here the summation of the voltage will be Vs minus Vs plus Vr plus Vl plus Vc. All of this equal to the voltage across the inductance, right? Which is minus VSL.
So this actual inductance is added into stray inductance?
Yes, this guy is stray inductance. The inductance of all these wires. Yeah, this is not in tape. We don't add it. It's there because of all this conductor, like transmission line model. We add the inductance and the capacitance between two conductors. For lumped element for at low frequency operation, the size of this circuit will be small compared with the wavelength. So the value of LS will be very small. Are you getting this? At low frequency, the wavelength is very large and the size of the whole thing here will be very small compared with the wavelength. So LS will be very small. You can ignore LS. If you ignore LS, this will be Kirchhoff voltage law, right? And if you don't have LS here, if you ignore it, this will be the same as KVL derived from Faraday's law. We can do the same for Kirchhoff current law, for KCL. So we can start with the continuity equation, which is the closed surface integral of the electric current density. We have here Gi and Gc, the embraced and the conduction current density. The surface integral over closed surface should equal to the enclosed current, the total current at this point, which should be very small volume, like a node in a circuit. Okay, and this guy has a unit of ampere per square meter. So this could be the summation of the current at a single point, which equal to the time rate of the decrease of the enclosed charge, partial Q, partial T, over the volume. So we can replace QE, the enclosed charge in this small volume, which will be like a node, and it will be something like this. So we have this is where the continuity equation is valid. So if you use the continuity equation here, you can assume that the integration of JDS equal to the current here, the total current. Okay, and when we can now replace the charge enclosed by some capacitance, which is stray capacitance as well. So Q here will be C times V, as we know, and we are going to find out that the summation of the current at this very small volume equal to negative CS partial V partial T. CS here is the capacitance between two conductors. It's stray capacitance as well. It's there because of the frequency effect. And if you have two conductors, you must have some capacitance in between, which is CS here. CS has been used in this relation, has been used here to replace the charge in this volume. Okay, as you can see, they are somehow comparable or similar in behavior. So I have replaced this integration JDS by the summation of the current, and I have replaced the QE here, the volume charge, the total charge by CV. The example here is to add the current. So we are going to add the current at this node, summation of the current. The current here is IR, IS minus IR minus IC minus IL minus IC. You just use the summation of the current here. Again, if we ignore CS, if we assume CS is very small at low frequency, this will be Kirchhoff current law. Summation of the current at this node will be 0. So as we can see, Maxwell equation can take us to circuit theory. Whatever we do in circuits are based on Maxwell equation. This is a comparison between the field relation and the circuit relation. So J here replaced by IR, sigma is like 1 over R, and the electric field can be like the voltage. This Ohm's law in circuit, this Ohm's law in field. This we call it Ohm's law, same as this guy. B can be replaced by the magnetic flux. Mu H will be replaced by L times I. This is displacement magnetic current density will be replaced by the voltage across inductance, as we have seen. So here's the integration of H will be like LIL. The electric flux density will be replaced by Q. This is like this takes you to the stored energy in capacitor. The stored energy in capacitor is based on Q and V. So the electric flux can be replaced by Q, and epsilon E will be CV. So as you can see, whenever you have epsilon, it is replaced by C and E by V. The displaced electric current density will be replaced by the conduction current or the capacitor current. This is the capacitor current, which is very similar to the displacement current density. So this is a field relation, circuit relation, and we have these are the parameters we have used in field theory and circuit theory. So the electric field can be replaced by V, voltage, H, current, ampere, D is the electric charge density, coulomb per cubic meter, the volume charge density. B will be the magnetic charge density if they ever exist. Okay, and in circuit theory, the magnetic flux will be replaced by Qm if it exists, if we assume it exists. The magnetic current will be replaced by magnetic current which is produced by external source, as we have seen before. This like the current in inductance or in coil wrapped around a magnetic core. This magnetic current, the electric current density will be replaced by the current through a capacitor. If you remember, the current in the capacitor between the two plates is based on partial E, partial T. And at the end, we have the displaced magnetic current density, which can be replaced by the voltage across inductance. Okay, mu here, mu is replaced by L, and epsilon replaced by C. So mu does represent how much magnetic energy can be stored. Epsilon represents how much electric energy can be stored in the system. This is the power, not the power relation. Again, the continuation for this. So J here would be replaced by I. And here we go for Maxwell Faraday's law. This Maxwell Faraday's law can take us to Kirchhoff voltage law. Summation of the voltage around any closed path equal to 0. And Ampere's law or the continuity equation can take us to the Kirchhoff current law, as we have seen. The power relation, as we'll see soon at the end of this chapter. So this is an instantaneous power at any time. It is the surface integral of the cross product of E cross H. And if you use the unit here, volt per meter and ampere per meter. Okay, so this will give you like volt ampere, which is power. This is instantaneous power comparable to the power across some circuit element, some resistor, which is VI. And we have also the dissipated power in resistors and circuits, which is I square R, or G times V square over R. The dissipated power in resistor. It's comparable to sigma E square over some volume. Okay, and we have also the electric stored power, which is in circuits 1 over 2 CV square. Here C will be replaced by epsilon and V by E. And this stored magnetic power, again, stored magnetic power does depend on mu, which is 1 over 2 Li square, the energy stored in inductor. So these relations are very meaningful to understand the relation between circuits and field theory. Any question? Can you stop this?